Displacement. Displacement is defined in physics as a change of position, which we write mathematically as big delta. So big delta will always be used to refer to a change. So in order to refer to a change of displacement, we will use delta x, which means that every time one goes from one position to another, there is a displacement. Now if we define a coordinate system, as usual, we'll see that we can represent this change of displacement, this change of position, sorry, by a vector. And therefore we will write displacement as vector delta x, which specifically says that we're going from position x1 to position x2. So in general, displacement is the final position minus the initial position. Now, let's choose a coordinate system such that the origin of our coordinate system will be centered at our original position, xi. In this case, we will be starting here, and let's say we want to go from this position to this position. The displacement vector can be represented by this arrow or this vector. Let's say this is our y, this is our x, this is my x final, this is my x initial, and therefore since xi is the same as my zero vector, my delta x in this particular case is nothing else than x final, which refers to the coordinate of this particular position xf. The nice thing about displacement is I could go from position initial to position final using this particular path, or I could use this path. Let's say I want to follow the x direction first, and then I'm going to turn around with an angle of 90 degrees, and I'm going to go up along another path 3, and this displacement is actually the same as the original one. Therefore the displacement 2 plus the displacement 3 is exactly the same as my displacement 1. Why? Because I started in both cases from xi and ended up in x final. Similarly for path 1, I started at xi and I ended at x final. So if we call and use the usual convention, okay, let's describe this as my vector A, let's describe path 2 as my vector ax, and this as my vector ay, then we're back to the original and usual way of describing vector and decomposing them in, let's say, two vectors perpendicular to each other. A is equal to ax plus ay is for us the exact same thing as going from, let's say, point A, point B via point C. Displacement AB is the same as displacement AC plus CD. This is displacement along path 1, and this is displacement along path 2 and 3. So the key to displacement is all we care is initial and final. We're not concerned about the path that we use. So we can write any displacement delta x as delta x1 plus delta x2 plus delta x3, as many as you want. You can decompose your change of position from this point to this point as either 1 delta x or with the sum of a bunch of little delta xi. As long as the initial and final position are the same, they are all the same displacement. So let's imagine in one dimension. I'm going along my x-axis. I'm starting at this point, let's say point A. I would like to change my position to this position. Let's consider unit vector I, and I'm gonna displace myself, let's say 1, 2, 3, 4, 5i. So my displacement dx is nothing else than 5 unit vector. So now I'm in position B. So this is the same as position vector AB. If I set up a coordinate system centered at A, then really what I've done is I took the position of B minus the position of A, which is again consistent with my definition, which was final minus initial. So in this particular case, my position of B is 5 minus position of A, which is 0 in the I direction, and that's how I end up with 5. Now let's imagine that now I'm turning around and I'm going to go to the opposite direction. So instead of still going towards the right, now I'm going to go 2 increments towards the left, to point C. C has coordinate of 1, 2, 3. B had the coordinate 5, 0. So now if I'm displacing from B to C, my position vector BC is position of C, which is the final position, minus the position of B, which is the initial position. Therefore, I will have 3 minus 5, and I'm doing this in the x direction. Therefore, I'm going to use my unit vector I. Therefore, my displacement BC will be minus 2i. So the sign, again, will tell me in which direction I'm going if I already specified a particular direction. So if I want to go from A to B and B to A, then really I'm going to displace myself along this particular vector AB, and then I'm going to displace myself back from B to A, and this will give me a 0 displacement. In this case, I went from A to B along this direction, and then I came back. Since my initial and my final are both 0, 0 minus 0 gives me the 0 vector. And therefore my total displacement is 0. So you can have a 0 vector. 0 vector expresses the fact that you started at one position and you came back at the exact same position, so that the final minus the initial end up being 0. Now let's imagine that I'm going to go on a loop again from position A to position B, then position C, and position D, and then position A. So I'm going to go from A to B, then B to C, C to D, and D to A. So my final displacement is going to be 0 because I end up at the same position from where I started. This will be equal to my decomposition of my whole displacement, which is position vector AB plus position vector BC, which is perpendicular to AB, plus CD plus DA. So my total displacement in this particular case is 0. However, the distance traveled is not 0. The distance traveled is this particular distance, which is the magnitude of my vector AB, which I will call and write AB, magnitude, plus the distance between point B and point C, which is the magnitude of vector BC, plus again the distance between CD, plus the distance between DA, and this obviously is not 0. So when I'm starting from one point and up to the same point, my displacement is 0 because my final is equal to my initial. And remember that when you deal with displacement, you only care about the final and the initial. However, if you're after the distance traveled, then what you need to do is obtain the magnitude of each displacement and add them up together. Since the magnitude of a vector is always positive, you always going to have a positive vector, a positive number. Therefore, the distance traveled really is a scalar, while the displacement is a vector. So that's when the notation becomes very handy, because this is a vector equation. This vector plus this vector plus this vector plus this vector give us 0, while you can rewrite this as magnitude, this scalar plus this scalar plus this scalar plus this scalar is not equal to 0. This refers to the distance traveled, this refers to the displacement. So this is one of the reasons we want to be very careful when we write displacement mathematically. We want to make sure that we use the arrow to specify displacement versus no arrow, which refers to the length of that vector displacement. So keep in mind that distance traveled is not necessarily the same as displacement. They could be the same, let's say, if you're traveling in one direction and you don't turn around. So let's say from point A to point B and point B to point C. Displacement vector, first one is AB, the second one is BC. So the total displacement AC is, I'm going to squeeze my little b in between. This becomes AB plus BC. This is my displacement, or position vector AC. In this particular case, my distance traveled AC is also AB plus BC. So the length of my position, of my displacement AC, happens to be its own magnitude. So that's going to be the only case where the distance traveled is going to correspond to the magnitude of the displacement. You have to go in the same direction all the time without turning back, or left or right. So that was the displacement.